consider the function f of x equals e to the minus x squared, right? So f of x equals e to the power minus x squared. What we need to do, show that f of x is decreasing for all x greater than 0. Part B, find the upper and lower sums that approximate the improper integral of f of x dx. So that's going to be, we're going to create a series, an infinite series. We're actually going to have two, one that gives an overestimate and one that gives an underestimate of the improper integral. And then we're going to write an inequality that relates the sums to the integral. So we're going to trap the true integral in between the upper and lower sums. Right, so to show that a function is decreasing for all x greater than 0, we need to consider the derivatives. If we can show that the derivative is negative for all x greater than 0, then that means the function is decreasing. This just comes from the calculus in the main course. So we're going to need f dashed x. F dashed x. Well, you can do long chain rule or short chain rule, but basically if you've got e to the power of f of x, then f dashed x, what you're going to, it's going to be f dashed x times e to the f of x. So whatever the derivative of this power is here, we're going to bring it to the front as a multiplier, and then we're going to keep the power the same. If you want to let u equal minus x squared and do it like that, that is fine too. But you should get, so the derivative of minus x squared with respect to x is minus 2x. Minus 2x times e to the minus x squared. E to the minus x squared. So that's the derivative, right? So then we need to show for x equals 0. So then we need to show that this is negative for all x greater than 0. If we just rewrite this, it might be a bit better. So remember, this is a e to a negative power. So that's the same as the reciprocal of e, 1 over e, to the positive x squared, which is the same as dividing by e to the power x squared. So I'm just going to rewrite that, minus 2x over e to the x squared. So if we write it like that, we can hopefully show that we're going to have a negative over a positive. So remember, for x greater than 0, so if x is positive, well, minus 2x will always be negative, right? Of course, we take a positive number, we times it by minus 2, which is negative, that will give a negative result, right? For x greater than 0, well, x squared will definitely be greater than 0 as well, and e to the x squared will be greater than 0. So we're going to have a positive divided by a negative. Positive divided by a negative equals negative. I probably don't need to write this bit, but never mind. So that proves that f dashed x is negative. F dashed x is less than 0 for all x greater than 0. Okay. Part B, write upper and lower sums that approximate the integral, right? So if we now know that this thing is decreasing. So if you have a function that's constantly decreasing, so I'm not going to actually attempt to draw e to the x squared, but let's just a general decreasing function, right? It's the same principle. If we start with the first, so this particular improper integral starts from 0, so if I call that a, so something like that can be 0. So this 0 can be a. Remember, we're going to have, we're splitting up all these things, so a plus 1, so 0, 1, 2, 3, so a plus 1, a plus 2, a plus 3, a plus 4, and so on, right? So basically, if you want to take a lower sum, then if you want to get the lower sum, then we always should use the right hand side. So if we start at a plus 1, and that would be the first rectangle, right? Then that would be the second. So you can see we're getting a clear underestimate of the actual area, right? So for our lower sum, is going to be the sum from I equals 0 to infinity of f of I plus 1. So we need to start here, I plus 1. So that is going to be the sum from I equals 0 to infinity of, well, we need to get our f of x, so it's going to be e. F of x is e to the minus x squared, so it would be e to the minus I plus 1, so it will be minus I plus 1 squared. So the thing that we're taking in is the I plus 1 squared. So that's our lower sum. Upper sum, well, that is going to look the same. So from I equals 0 to infinity, for an upper sum, we want to always be taking the left hand side, so we can actually start at 0 and then we're going to do 1. So we're going to do f of I. So then we're going to do f of 0 plus f of 1, as opposed to this one where we did f of 1 plus f of 2 plus f of 3 and so on. Always the right hand sides for this, always the left hand side, because the function is decreasing. So that is going to be the sum from I equals 0 to infinity of e to the minus I squared. Okay, for part C, which I haven't given myself a lot of room for, we need to write an inequality that relates the sums in B to the integral, right? So we have these two sums. So we've got the true integral, which is the integral from 0 to infinity of e to the minus x squared dx. So that's the true integral, right, in the middle. So we know it's less than the upper sum and it's greater than the lower sum, and we just write those in. So the lower sum was the sum from I equals 0 to infinity, this is part C by the way, of e to the minus I plus 1 squared, and the upper sum is the sum from I equals 0 to infinity of e to the minus I squared. So we know that the true value of the improper integral is definitely less than this and more than this.